Hello, my name is Victor Lortz. I'm a software engineer at Intel Corporation, and I'm going to be talking to you today about some research that my advisor and I did at the University of Michigan as I was working on my dissertation project. And that project was an object-oriented real-time database system, and we used a lot of the techniques I'm going to be describing today in the implementation of that, and they're very useful and important to the success of the project. So as sort of an outline of the talk, first of all, I'm going to motivate the problem, explain what we were trying to solve, and then explain the contracts method that we came up with and what that exactly means, and some of the implementation issues. And I'll describe how the contracts can be used to customize the service classes, say of a library, a database, or what have you, at runtime. And then I'll explain some of the advantages of using exemplar-based techniques for customizing service classes, and then I'll conclude. So first of all, the usual approach to implementing a software service such as a database or operating system would be to define a set of abstract interfaces to the services as sort of a black box interface, and then implement that interface with some concrete instance of the service and hide all the implementation details from the clients. And there's advantages to that with respect to encapsulation and code reuse. But there are also some significant drawbacks to the black box approach. First of all, there's no concrete implementation that's ideal for all clients. So you might, when you go ahead and implement a service abstraction with some concrete approach, inevitably you're going to be biasing the performance of that server according to your preconceived ideas of how the service is going to be used. So it will work best for certain access patterns of the server functions. And that will cause clients that don't happen to follow that same access patterns to get perhaps a very poor performance from the service. And because of that, the black box abstraction needs to be improved somewhat. With object-oriented techniques, you can actually have multiple different concrete implementations of a service. And then each one of those implementations can be tuned according to the particular application's user patterns. And so you don't have to have just one implementation of a black box. You can have multiple concrete implementations of a service. There's another significant drawback of the black box, though, and that is sometimes black boxes hide too much information. Clients need information about the performance of the different methods, or they might need to know how the server will respond if there's concurrency and other characteristics. And so some of these characteristics of the server are hidden by the black box abstraction. And so there's no way that a client will really know how the service will perform. And without that knowledge, they're just sort of taking a chance that the server is going to do what they want it to do. So if you use object-oriented techniques to address the first problem and have multiple different concrete server classes, then you can introduce some additional dependencies, which is sort of another drawback of taking that approach. Those dependencies I'll illustrate with this next slide here. Here we have an example of an abstract server class that the clients 1 and 2 are using. And clients 1 and 2 may have very different access patterns. They may not even use the same methods of the server. And so underneath that are some concrete examples of server implementations. And server A may be implemented so that it works best with client number 2, and B may be implemented so that it's most suited to client number 1. Unfortunately, if client number 1 has to explicitly say that it wants server B, and client 2 has to say that it wants server A, now we've introduced a dependency on the specific server classes. And so that makes it difficult to extend and enhance the class library. And it doesn't really solve the problem either of knowing what the actual performance of server A or B are going to be. So there's no guarantee that the clients have that they will really, all of their requirements will really be met. And ideally, what we would like to be able to do is have a client specify what its preferences are and what its requirements are to an abstract server class, and then have that abstract server class automatically select from the concrete classes the one that's going to best meet the needs of the client. And in fact, that's the approach that we're taking. I'm going to explain how we actually do that next. So our technique we call contracts, and this is taken by analogy to contracts in civil law, where you have some document that expresses the requirements of a client. And a server, if the server accepts the contract, is saying that it is willing to abide by whatever restrictions are in that contract. And so for some examples taken from the domain of my real-time database research, we might have a contract that says that you want this object to be persistent or to have single writer concurrency semantics so that the server could be tuned to that type of concurrency control. Or you could express an actual deadline on the execution, the performance of a particular method of the server. So we have a write element takes less than or equal to 50 microseconds. And these are all expressed in our implementation as character strings. And each one of these examples would be a clause in an overall contract. So you could have a list of these specifications in the contract that the client uses. Another example of a contract would be to find an element where you're perhaps finding something in a data structure where the execution time of that find is proportional somehow to the size of the data structure. So you could express the complexity of that, the runtime complexity, or you could express space complexity, all this sort of thing you can express in the contracts. So for an example of actual code that a client application might use in using this technique, they can specify which service class that they want to use. And that would be a base class of a service hierarchy where you have the concrete classes implemented underneath and derived from that base class. And you specify as well in the constructor to that object a list of contract clauses. And each clause represents a requirement that the client application has, or it could express a preference that it has that would bias the service selection according to one of the concrete service classes. And so once the object is constructed successfully, and if it can't meet if there's nothing in the library that will meet those requirements, then it won't get constructed correctly. But if it is constructed correctly, then you could also use the contracts to query information about the server. So for instance, if we had specified that the find operation has to be less than or equal to order of log n, then you don't know the actual performance of the find operation. So you could actually call a method on the object called query time and find out what that particular object's performance will be for that operation. And that would be dependent on the size of the object. So you could determine at runtime what the actual performance is, not just the computational complexity of it. And so contracts can be used to express constraints during object construction, and they can express information at runtime that has to do with the performance of the server. So the contracts express meta-level information. They express information about how the service will be provided. They're different from the server interface specification. One advantage of contracts is that they make the dependencies explicit. You're no longer depending on the performance being sufficient just on the basis of reading some documentation. You're actually specifying in the code what your performance requirements are. And so you don't have these implicit dependencies creeping into your applications where some new revision of the library may invalidate those assumptions. Another aspect of contracts is they can be used to enable automatic customization of server objects. And I'm going to be explaining how that's done next. Furthermore, they can, as we've seen, they can both support specification of requirements and runtime retrieval of the server characteristics. So here's an example of how contracts might be checked by a particular server class. This would be a concrete server class. This is having one server class checking the contract of one application. And we can see the class hierarchy. We have the abstract server class and a concrete server underneath that, and then a customized one that's been added. It's also a concrete server class. And when it gets past the contracts, it iterates through the list of contract clauses and checks each one individually. Now, when you derive your own customized server class, you only need to know about the new contracts, the new clauses that are affected only by your customization. So you check those. If you encounter a contract clause that you don't recognize, you may have inherited the ability to meet that constraint from your superclasses, so you can just defer the checking to the checking functions of the server classes and chain up the class hierarchy. So that's an implementation approach that can make it easier to derive new customized server classes. And we've seen now how an individual server class can check contracts and decide whether or not it satisfies the constraints that are passed to it is in a contract. Now I want to talk about how this idea is extended so that a class library can actually select the server class that best meets the requirements of an application's contract. And so a lot of the ideas here were borrowed from James Copleen in his excellent book on advanced C++ programming. And the approach we're taking is an exemplar-based approach, where exemplar objects, which are prototype objects for specific concrete classes, are used to represent all of those classes at runtime. And each prototype object has a clone method associated with it. The clone method is used to make a copy of that object. So in this example, the client specifies one of the server classes. And that server class is actually a base class of a server hierarchy that has a lot of concrete classes underneath it. And that server class, when its constructor is called, just like we saw with the examples of the contracts, the contract is passed to the constructor. And the class that has the constructor is the base class, which is actually a class factory. And it has associated with it a list of the exemplars of all of the concrete classes that are derived from it. And so it takes that contract and submits it in turn to each of the exemplars of the derived concrete classes. Those classes, those exemplar objects, examine the contract and make a bid on it. Once all of the bids are in, the class factory can decide which one to instantiate. Then it takes that one and calls the clone method to create a copy of it and returns that object to the client. So by this process, the client requirements that are expressed in the contract get mapped onto one of the concrete implementations of that service. But the client never knows which one is actually chosen. So none of the dependencies that would otherwise creep in to the client code end up there, because the only dependency that the client has is on the abstract interface to the class. One of the questions that arises is, this is an interesting technique. How much overhead is there involved in this? And of course, that answer depends on how it's implemented. We took, in our real-time database work, we took a fairly straightforward approach and literally had an iteration over all of these exemplars. It could be possible to take the contract and use it essentially as a key to search through say a tree, a discrimination tree or something, where the exemplars are organized in a data structure other than a list. And so you could use the contract to search and eliminate, on that basis, most of the exemplars from consideration. And then you would only actually submit the contract to a few exemplars. But like anything, the more complicated your algorithm is, the more difficult it will be to implement. And for most cases, at least in our cases, it was acceptable just to iterate over the exemplars. Another point I wanted to make is that these exemplars don't necessarily correspond on a one-to-one mapping with the different concrete classes. You could have a concrete class that's parameterized by some variable and have more than one exemplar of that class be in the exemplar list. And so you could customize the service by parameterizing these different exemplars, and then when you clone them, they will already know which optimization to use. So there's a lot of flexibility in this approach. Another issue is how difficult is it to implement this contract checking in a class library? Because if you're a class library implementer, that would be of interest to you. And the answer is you can implement most of the machinery for doing this contract checking in the base class. So all of the classes of all the different service classes in the library can inherit that basic functionality from this base class. And when you are implementing a new server, you only need to override just a few methods, 2 or 3 methods you have to implement to enable all this mechanism to work. So I want to discuss now some of the advantages of this exemplar-based approach. First of all, the applications see only the abstract factory classes. they don't see the particular implementation classes. So again, that dependency is removed. Furthermore, the class factories don't need to know their own contents. The factory could have additional server classes derived from it in the future, and they can be automatically added into the factory just by appending their exemplar to the exemplar list. And the class factory code never needs to be changed or never needs to know about the existence of these new classes. So the client applications, if they determine that the factory doesn't contain a class that meets all their requirements, they can just subclass from one of the classes in the library, customize it to their own particular needs, implement the contract checking part that will indeed show that they're satisfying their requirements, and just merge that into the original class factory. And none of the library code has to be changed at all for that to happen. Furthermore, because none of the concrete class names propagate into applications, it's much easier for the class library to be customized and restructured after the fact. So even if you have existing applications that are using that class library, you can restructure the library without breaking existing code. For an illustration of this, you can see an example where this client is using an abstract server class. It passes the contract to it, and the original implementation of the server has, say, just two classes, A and B, that are the concrete classes in the library. And so the contracts for the different clients will be mapped onto either A or B. And then suppose someone comes along and they want to release a new version of the library and change the library so that instead of having class B, we have classes B and B prime and B double prime. So the class B is removed entirely, and then a new class C is added as well. Well, it's possible to do this sort of restructuring if you use this contract and exemplar-based approach, because none of the dependencies on B have propagated into any of the clients. Furthermore, now any of the clients that submit their contracts, even if they originally mapped onto either A or B, now those contracts will map onto one of the four new classes, and the clients will never know the difference, except they will get improved performance if the library implementer has done a good job of implementing these other classes. So I want to just talk a little bit about these techniques in the context of meta-object protocols, because the meta-object protocol researchers have been addressing essentially the same problem that we were addressing. A meta-object protocol is a protocol by which clients can specify how they want a service to be implemented. And that's essentially what we have with our contracts approach. There are two different types of meta-object protocols that have been identified by Gregor Kixalis and others at Xerox PARC. You can have a declarative meta-protocol, which is essentially a selecting of one of a predefined set of concrete service classes. So, for example, a declarative meta-protocol might be, well, I want my user interface to be have a motif look. And so it selects from the motif user interface classes. An imperative meta-protocol is a meta-protocol in which the clients actually specify how to implement some aspect of the service. And so, for example, you might specify what the sort algorithm should be for a server that does some sorting or something like that. In the context of our techniques, we actually show both a declarative and an imperative meta-protocol, because the contract is a declarative meta-protocol. It's selecting one of a set of predefined server classes. But the ability to subclass and create new concrete server classes and implement them into the library's class factories is an example of an imperative meta-protocol, because you can override and implement the methods that you're interested in explicitly, and your client, your application program can do that and merge it in, and then the declarative meta-protocol will map onto that one if it meets those requirements the best. One of the advantages of using a declarative meta-protocol, and that's really one of our main focuses is these contracts, is that it's much more convenient. So you're not requiring applications to implement their own server classes. They only have to do that if one of the existing ones doesn't meet their needs. So there's a lot of advantages to having both declarative and imperative meta protocols. So in conclusion, we've described a set of techniques whereby applications can specify in contracts their requirements and pass those contracts to class factories that will automatically construct server objects. This approach combines the advantages of declarative and imperative meta protocols. Another major advantage of our approach is that the dependencies on server behaviors that would ordinarily might be just implicit in application code can actually be made explicit by the contract, and so they aren't just hidden in the applications, and you end up with potentially more robust client applications that way. Our techniques are especially useful in domains where you have very critical constraints, where you might, like in a hard real-time system, you absolutely need to know what the performance is going to be, and you can't tolerate missing any deadlines. The applicability of our approach will depend on what exact server class it is and how it's going to be used by applications. You wouldn't want to apply our techniques to servers that would only be used once and then destroyed again, because there's overhead that has to be amortized over subsequent server use. And so another question, I guess, on the implementation of it is, well, do we have to do all this processing at runtime? Because if you can do the contract processing at compile time, then you wouldn't even have to worry about the runtime overhead. And I think, in fact, it could be possible in some cases to do compile time or possibly link time contract checking. In our real-time database, it wasn't feasible because we had multiple applications that were sharing the same objects, because this was a database for a multiprocessor system. So we had to do our contract checking at runtime. But I think it could be possible to extend it to work at compile time in some cases. But you definitely don't want to just apply this method indiscriminately, because there's some overhead involved. There's some additional work required to implement the concrete classes. There's some additional runtime overhead involved. So you would only want to apply this in cases where you had very critical constraints, where you wanted to check all the dependencies and make sure that none of the constraints of your application would be violated. Or if you have a case where you have a set of server classes where there's a big difference in performance between tuning to one pattern of usage and tuning to another one, and you don't want to propagate any of those dependencies, if you want to be able to restructure the class library like we've described, then the applications can benefit from using our techniques. Thanks very much. You can always contact me at Intel or my advisor, Kangshin, at the University of Michigan.